Okay, so it's 2 minutes after the hour, so I guess we should get ready to get started. We might have some more people joining us shortly, but today it's my pleasure to introduce Dr. Jan Henneco. So Dr. Henneco is originally from Leuven, did his bachelor's and master's at KU Leuven, the latter supervised by Timothy Van Riet and Joy Mumbark. Um, and then moved on to the PhD at the Heidelberg Institute for Theoretical Studies with Fabian Schneider and Saskia Hecker. And currently is a postdoc with Dominic Bowman at Newcastle University. So today Jan will be telling us about asteroseismic signals of massive binary interaction products. So thanks a lot for joining us, Jan, and please take it away.
Thanks, Alexander. So yeah, quite a long title for today, and believe me, it was even a bit longer before, but I shortened it. So I decided to break it up in its different components. Today we're going to start by talking about, if the controls want to work, massive binary interaction. So binaries, especially the massive ones, I don't think I need to tell you at this point that they are common. So multiple stars in general are relatively common. And this multiplicity fraction that you can see on the plot over here increases quite strongly with mass. So for B-type stars and for O-type stars, binarity or being in a triple or in a quadruple is actually more the standard than being in a single star. It was also found relatively recently that about 70% of massive binaries interact via mass transfer. And this is a bit of a double-edged sword because on the one hand, if you can get good data for a binary, you can get the masses and the radii for such stars in a model-independent way, which allows you to put even better constraints on stellar structure and evolution theory. On the other hand, these interactions that I just talked about, they will severely complicate the evolutionary picture because it will not be single stellar evolution anymore. So let's focus a bit more on this mass transfer, this interaction between the two stars. So we'll have a donor star, the one that has swelled up and is now donating mass to the other star, which we call the accretor. And these accretor stars are going to be one of the kind of the subject stars of today. So some chemical, what I'm saying, chemical, some observational evidence of stars being accretors is that you could have chemical enrichment because they accrete material that is enriched, for example, CNO material. They can rejuvenate, although it's not always clear if and when this happens. And then they will spin up, so they don't only accrete matter, but also angular momentum. They will spin up and they might appear as BE stars, for example. A more extreme outcome of this mass transfer is that the binary gets into a contact phase. You have this peanut-shaped contact binary over here, or if one of the stars, the donor star, is a more extended object, then you can get what we call a common envelope or a classical common envelope phase. But in the end, what can happen in both cases is that the stars merge. And what we found during my PhD is that between 15 and 40% of mass transferring binaries actually merge, and they leave behind a merger product. These merger products are the second type of stars we're going to be looking at today, because them being single stars after they merge are ideal scapegoats for whenever you find an observation that you can't explain with single star evolution. So I've already mentioned a bit of the observational evidence of accretor origins of a star, but let's look a bit at observational evidence of merger origins now. So one of these merger products, or merger products in general, it has been theorized and also been shown with simulations that they can have strong surface magnetic fields. They could be slow rotators, although the debate on that is not really settled yet. And again, because you're putting two stars together, you can get chemical peculiarities on the surface that might be able to help you tell that this is a merger product or not. If you have clusters, if you do clusters observations, you might find some stars that are too massive to explain. So stars that should have turned off the main sequence here already and moved up to the top right. We call these blue stragglers. And so they are stars that are thought to have rejuvenated, again, because two lower mass stars have been merged into one more massive star. And so this brings me to what I've started calling the merger and the accretor hypothesis. So basically, if you find a combination of peculiar features that do not match the single star evolution picture, it is often what people often hypothesize that these are merger products or accretion products. And sometimes this really works very well. There's a great example from a few years ago where a binary was discovered, and one of the stars in the binary seemed to be a lot younger than its component, than its companion. If you assume that both stars are born together, this is something you do not expect. There were some outflows around this star, and it was also a strongly magnetic star. So that's a great example of a star that is very likely going to be a merger point. But this does not always work. Let's say you have a cluster or you have a whole sample of stars. We want to be able to say, for example, if you want to test single star evolution, these are merger products, these are accretors, and these are single stars. And we want to be able to identify them. And that's not always super straightforward at this point. But luckily for us, it's not only their surfaces that are peculiar, as I just explained, but their interior structures could also be peculiar because of chemical enrichment and rejuvenation. So they are ideal targets for asteroseismology at a study of these stellar interiors via stellar pulsations. So the question for today is, can we use and how can we use asteroseismology to identify these binary interaction products, so merger products and accretors? So that brings us to the asteroseismic part of the title. And to get everyone kind of up to speed, let's do a asteroseismology crash course. Stars oscillate during different times of their life, and if you want to mathematically describe these oscillations or pulsations, we typically use spherical harmonics in the simplest non-rotating case. Such a spherical harmonic you can describe with three quantum numbers. So first we have the spherical degree L. So we see a spherical harmonic over here. That's how the deformation on the star looks like because of a pulsation. It's exaggerated, of course. The spherical degree L is going to tell us how many of these white nodal lines there are. So nodal lines are lines where there's no displacement of the stellar surface. In this case, there are 7. Then we have the azimuthal order M. That's how many of these lines also cross the equator. So in this case, those are 4. So we already have the morphology of the mode at the surface. And then if we look inside the stars, there are also several nodal surfaces. So surfaces within the star where the pulsation does not cause any displacement. There's going to be your radial order N, and this is going to be important for later. So keep that in the back of your mind, please. And then, of course, there are the frequency or the period and the amplitude of a mode. Now, that's not all. There are different types of modes, and we classify them based on their restoring force. So the two most, let's say, famous modes are the pressure modes, where your pressure gradient is the force that is actually sustaining your mode, allowing your mode to propagate throughout the star. These are sound waves. Yeah, these are sound waves. And then there is the buoyancy force, which is essentially Archimedes' principle. So you have a fluid particle that can oscillate around its position, but this can only happen when the star is stable against convection, and these stars we call gravity modes or G modes. There are other types of restoring forces, such as the Coriolis force when a star is rotating, call them inertial modes, and the Lorentz force can also be restoring force in magnetic stars. Now, a very important point for today is that's going to come back a lot of times, is that the structure of the star determines where different modes can propagate within the star, so where they're sensitive to and what kind of information we can get from them. And the structure of the star is also going to influence the mode properties themselves. So this is the power of asteroseismology, essentially. If you want to make this a little bit more quantitative, I have here what we call a propagation diagram, or at least a sketch of a propagation diagram. Basically, based on some characteristic frequencies within the star, like the Brunt-Väisälä or the buoyancy frequency, which is a purple one over here, and then the Lamb frequency, which depend on the sound speed in a star. These frequencies are going to determine where certain modes can live. So our gravity modes, for them, we know that they can only live in regions or propagate in regions within the star where their frequencies are lower than the Brunt-Väisälä frequency and the Lamb frequency. So we have this purple shaded region where these gravity modes can live. Since they are driven, or they are not driven, they are sustained by the buoyancy force, they cannot propagate in convective regions, or at least they will decay when they enter such a region. So that's also important to remember for today. And our P modes, they can only propagate in regions where their frequencies are higher than these characteristic frequencies. Now, again, and I'm going to keep dropping all of these things you need to remember, but they will all make sense later. So another important thing to remember is that the example I've drawn here is of a main sequence star with a convective core on the main sequence. And what these cores do is that they tend to shrink and leave behind a chemical gradient. So in general, any structural feature, such as a chemical gradient or sharp transition, will influence your Brunt-Väisälä frequency profile and have an effect on the pulsations, for example, trapping them in a certain region of the star. Okay, so before we get into some of the results, a quick, very easy flowchart of how many of these studies that I'm going to discuss now have been done. They're all theoretical predictions of binary interaction product asteroseismology. So what we basically always do is you take a stellar structure and evolution model. It can just be a 1D model, for example, with MESA, or if you're lucky, for example, you're looking at a merger product and you have a 3D simulation of a merger, you can map that into 1D, put it into MESA and evolve it to the point where you're interested, where you want to look at how the star is going to pulsate. So throughout the evolution in MESA or any other code, it's going to output profiles, which are essentially snapshots of the structure of the star at a certain point in time. And you can take this structure and essentially perturb it. You're going to solve the oscillation equations, for example, with a code like gyre. And from that, you're going to get your asteroseismic properties out. So that's basically the idea of the things I'm going to show you now. Okay, so we get to, well, the bulk of the title now. We're now going to look at these peculiar asteroseismic signals of massive binary interaction products. And then what we can learn from them part, I hope to kind of sprinkle through the presentation while we go through it. So asteroseismic predictions for merger products. Let's start with merger products. There's two types of merger products that I want to discuss today. The first one is the merger product between two massive main sequence stars, which gives you another more massive main sequence star. The second type of merger product I want to look at is a blue supergiant, and not just any blue supergiant star, but a blue supergiant in a sense that the star has just left the main sequence, just stopped burning hydrogen in its core, and has just jumped onto the Hertzsprung gap. And at this point, the star is rapidly expanding and it merges with its main sequence companion. What this is going to give you is another blue supergiant star, and I hope to show you later, it's not going to be any blue supergiant star, but one with very peculiar properties. But let's start with I would say, the simplest case of two main sequence stars merging into one. Now, I told you before, sometimes you're lucky, and then you have a 3D simulation of a merger product or any kind of star with special features that you want to study, something that you can't easily reproduce in 1D. And in this case, I was lucky. So this is a kind of snapshots from the 3D simulation from Fabian Schneider and his collaborators, where they merged two massive stars, two massive main sequence stars. And basically what you see here is the amplification of the magnetic field during such a merger. I remember in the beginning I told you that mergers are thought to be responsible for these magnetic fields in such massive stars. Now, as I also said before, what they already did in 2019, 2020, and what I did afterward myself is that you take the end product of such a merger simulation, you map it back into 1D. You have to make a couple of assumptions, but you map it back into 1D, and then you can follow its evolution again in a code like MESA, for example, right? So we see that the star goes through some relaxation phases, but in the end, it ends up here again on the main sequence, and it follows a relatively normal main sequence evolution path. So from here, I would say it's hard to identify this as a merger product. So we're going to focus on this main sequence part as well. So, well, we're looking at models, so it's a bit easier. We can already immediately look inside of the star and actually see what happened during the merger and see how that's going to affect the asteroseismic properties. So what happened in this simulation is you had an 8 solar mass star and a 9 solar mass star. The 9 solar mass star, being slightly more massive, is also a bit more evolved, so it's a little bit more enriched in helium than its lower mass companion. Now, the cool thing about this merger product is that opposed to as opposed to what we expected, that the less buoyant, the more dense 9 solar mass core, the core of the 9 solar mass star ends up in the center. It's actually the less evolved core of the 8 solar mass star that ends up in the center of this merger product over here, which means that you already get a layer around the new core that is enriched in helium. So eventually the star becomes a main sequence star again over here, and it gets a convective core again. But that's not all of it. Before it becomes a main sequence star again, our convective core makes kind of an excursion in the sense that it grows in size for around 1,000 years, and then it shrinks again. And this may seem like a kind of a numerical artifact, but what we found is that this is actually something inherent to the fact that this is a merger product. So the chemical composition in the core isn't entirely what it should be for CNO burning, and it's also a little bit too hot in there. So as a way of kind of relaxing the core, it grows in size and then shrinks again, which is going to affect our chemical structure. So already two features here that are already different from what we expect from a genuine single star, so a star born as a single star. Let's make this a little bit more quantitative. So this is a tulips plot now, where we make 2D slices of 1D models essentially. But what this tulips plot nicely shows is that indeed, if you look at the helium mass fraction here from blue to yellow, is that our genuine single star on the left here, it's pretty basic. You have the kind of the pristine envelope over here and then the convective core. But for our merger product, we see the enrichment of helium from the fact that this core ended up in the envelope. And then we see the effect of this little excursion of this transient convective core. So if you know anything about, or I hope you know something about asteroseismology at this point, but if you already have a little bit of a feeling about it, you might already be excited of what kind of pulsations we're going to get out of such an object compared to such an object. One first result we already found is because the envelope is enriched in helium, the pressure modes, which live mostly over here, are already going to be shifted. Their frequencies are already going to be a little bit different compared to a single star, a genuine single star. Okay, so there were those were the pressure modes, but there is something with the G modes, a very powerful kind of diagnostic that we can use in asteroseismology that tells us a lot about the near core region of such a star. You might have heard about it before. It's a period spacing pattern, but I decided to also get everyone up to speed about it because it's a very powerful tool within asteroseismology, but it's not always super easy to understand from the beginning. I've drawn 4 different modes here, represented by a string that is vibrating, and they all have a consecutive number of radial nodes. So the nodes are the white dots over here. What we can do if we observe these modes in the star, so typically when one of the modes is there, the overtone, so the modes with higher n values will also be there. So if we can observe these and we measure the difference between the mode periods, we get this delta Pn. Now, the asymptotic theory, which is a theory that holds for radial orders that are a lot larger than 1, so this is a bit of a simplification, tells us that in a chemically homogeneous, non-rotating, non-magnetic star, where the modes also don't interact with each other whatsoever, these differences between the pulsation modes should be constant. So they should be the same. And this constant value of delta P, or the asymptotic period spacing, is related to the size and the shape of our G-mode cavity. So this thing alone, if you already can get the mean value of these spacings from a star, it already tells you, for example, something about the size of your convective core, because this is going to affect the size of your G-mode cavity. So what is a period spacing pattern? And a period spacing pattern is essentially when we take these differences in periods and plot them against the mode period or the radial order. But in this case, for a chemically homogeneous non-rotating non-magnetic star without mode interactions or mixing, you would get a straight line because I just told you the periods are equally spaced. But remember, don't remember, stars are typically not chemically homogeneous. From the moment that they evolve a little bit, their core recedes and they leave behind a chemical gradient, which causes this peak that I showed you before in the Brunt-Väisälä frequency. Now, what such a peak does, it basically acts kind of as a speed bump for certain modes. So what it's going to do is going to affect certain modes, change their period, cause some of the periods to be closer and some of the periods to be faster. So in a real massive main sequence star, we're going to get a period spacing pattern that kind of follows the behavior of a horizontal line, but there are these kind of bunny hop pattern variabilities in there. And so this also is going to give us a lot of information about the chemical structure in the near core region. So that on its own is already very powerful. But this is for a genuine single star. What if we now look at the case for our merger product that we started off this section of the talk with? And so I've plotted the Brunt-Väisälä frequency profile for our merger product now. And so the single star and the merger product here, the black and the orange model, they look exactly the same from the outside. They have the same luminosity, same effective temperature, same radius. But as you can see from the Brunt-Väisälä frequency profiles, their interior structures are different. So we have a similar peak over here because our merger product is again on the main sequence and its core is also receding. So that's single star physics. But then we have this additional peak over here. Let's look back at our interior structure and remember that we had this kind of gray layer here, this kind of gray homogeneous layer, which is a relic of this transient convective core, of the fact that our convective core after the merger made a little excursion, became a bit bigger for 1,000 years and then shrank again. So very strong feature in our Brunt-Väisälä frequency profile. So let's see what that does to our period spacing pattern. We have in orange the same period spacing pattern as before for the single star. And then in black, we have the one for the merger product. And we see that it does a similar kind of bunny hop pattern, but there are these additional dips in there. So additional components in the variability of the period spacing. So that's already the first, besides the shifts in the periods in the pressure mode frequencies that I talked about before, this is the second feature that we discover that is different between merger products and genuine single stars. Another thing we looked at is we see these two lines here. They're essentially these the mean values of our period spacings, because this is also something you can typically measure. And what would be nice if this difference between the mean values is large enough, so we can say, for example, well, this star has an abnormally high mean period spacing value, or an abnormally low mean period spacing value. But we see that it's about on the order of 100 seconds, which is just enough to measure the difference. So with our even with our current telescopes, we could be able to say, well, there is a difference there. But if we look at this kind of little experiment we did, we have the yellow cross over here. That's our merger product that has a certain mean period spacing value. And we draw a typical, let's say, observational uncertainty box around it. So in terms of the luminosity and of the effective temperature. So in an ideal case, these single star tracks that you see on the back here, they all should have different colors than our yellow cross over here, because then we could really say, well, wow, this merger product really pops out. If we have an observation like that, this must be a merger product. If this star pops out, this must be a merger product. But unfortunately, what we see, at least for this specific merger product that we modeled, is that there are stars, genuine single stars, very close, that have similar period spacing values. So, well, unfortunately, it doesn't seem like a kind of a good diagnostic right now to identify merger products. But who knows? There's more merger products to explore with different configurations, for example. Okay, that was everything for the main sequence merger product. Let's move on to the blue supergiant one. And why specifically such a blue supergiant? Well, it all ties back to this blue supergiant problem that you might have heard about before, right? So you can see here from these HRD tracks, this figure from Castro et al. 2014. So all of these markers you see here, I think they're separated by 10,000 years. And so when a massive star evolves off the main sequence, it really quickly moves over to the red side of the HRD and becomes a red supergiant. So in principle, we should not expect to observe any stars in this region over here because single stars don't tend to stay there for very long. But if you overlay this with kind of a density map of observations, we see that there is quite a few stars that live in this Hertzsprung gap. So that's the blue supergiant problem. Our single star evolution theory tells us that there should not be any stars here, or not a lot of them, but we do see quite a lot of stars in this Hertzsprung gap. So yeah, that's essentially what I wanted to highlight. Okay, but so what Earl Bellinger and his collaborators did in 2014 is they took this blue supergiant problem and they asked themselves the question, can we maybe solve this blue supergiant problem using asteroseismology? Is there any, if we would go up and observe, we get the time series data for these blue supergiants there, is there any feature in their pulsations that we might be able to use to say, well, we can solve the blue supergiant problem because they're all maybe merger products or maybe something else? So what Bellinger et al. Did is they computed a set of models and kind of tracked their behavior in this blue supergiant box here. So first, they started with classical Hertzsprung gap stars, or single stars that quickly move from left to right. They also considered the fact that maybe the cores of these main sequence stars of our models should actually be larger. So they created a bunch of models with overmassive convective cores because they tend to extend into this blue supergiant region. They also considered the fact that stars, depending on what physics you put in there, tend to, when they are red supergiants, sometimes make what they call a blue loop, where they move back to the blue and then move back to the red. So they could also populate this gap over here. And then finally, as I explained a few minutes ago, if you take a star that has just left the main sequence and you merge it with its companion, it tends to produce these long-lived blue supergiant models. So single stars that tend to spend a lot of time in this box here where we find actually a lot of stars. So those are our binary merger products over here. So one of the main results from this Bellinger study, which I find really cool, is that a classical Hertzsprung gap star, the fact that they move from the blue to the red relatively quickly means that their structure is also rapidly changing. And the star is rapidly expanding and becoming a red supergiant, meaning that the mode cavity, where our modes can propagate, also changes rapidly. And so what they predicted is that if you want to see if these are classical Hertzsprung gap stars or anything else, you do expect the rate of change of the frequency. So if you we get the mode frequencies of these stars across different years should technically be observable. So any changes should be observable between 1 to 4 years. So we would be able to at least pick out the classical Hertzsprung gap stars. If you look on the x-axis over here, which is our mean period spacing, again, they find that if you take the populations as a whole, at least, that there doesn't seem to be much of a difference between our genuine single stars over here and our merger products, and also the blue loop stars over here. So there doesn't seem to be anything in the period spacing, or at least the mean period spacing, that might be able to help us identify merger products. But again, this is if you compare a population to a population. So what we tried, so right at the time that this study came out, I was working on a similar project where we tried to do it kind of from another angle, where we were going to do a model by model comparison. So we're going to try to answer the question, if you have two stars in exactly the same location in the HRD, can we distinguish them then based on their period spacing? So unfortunately here, no fancy 3D model to start with. So what we did is one of these 1D methods to create a merger. So we evolved the star of the main sequence. It's here in the Hertzsprung gap, and then we merged it by essentially creating a lot of material in a very short time. So for these kind of stars, this is actually a way to get something that looks like a merger product structure relatively cheap. And as expected, and this is something that we also know thanks to our bachelor student at the time, Julian Salim, who explored the whole parameter space. So I'm saying as expected in the sense that thanks to his bachelor thesis, I knew that such a configuration of a 6 plus a 2.4 solar mass star would get you a long-lived blue supergiant merger product, right? Because 1 million years after the merger, our star is still here in the blue side of the HRD. As I said, we want to compare with a genuine single star in exactly the same location of the HRD. So we computed a genuine single star model that crosses the Hertzsprung gap around, like basically that crosses the track of our long-lived blue supergiant merger product over here, right? So we're going to compare both models over here. This plus symbol over here, let me go back real quickly. This is 1 megayear after Tom. So just to give you an idea, our genuine single star has already evolved into a red supergiant at this point. So we're going to compare the stars here when they're in the same location of the HRD. Again, that's the advantage of doing theory, is that we can just look inside of our models and see what the structures are. And we found something really cool, actually. So if you look at the structure of our genuine single star, as we expect, there is no core hydrogen burning anymore. There's no convective core anymore. There is still some subsurface convection, but let's not draw that for now. For all intents and purposes, this is a fully radiative star, which is what we expect from single star evolution theory, meaning that the whole star is essentially a mode cavity for our gravity modes to propagate in. If you look at a merger product, the reason why it's staying here for a long time is because of the merger, it's old enough to already ignite helium in its core. And at the same time, there's also this convective shell that appeared in this model. So the star is basically at these sides, it's evolving, it's burning helium here in the blue side of the HRD. And instead of one big mode cavity, we have a smaller mode cavity over here, and then a separation, because here our G modes cannot propagate, and then a bigger mode cavity over here. So again, looking at these structures, I hope you're a bit excited about what the asteroseismic properties should be of such a merger product. Let's look at period spacing patterns again. Same as before, we expect them to be a straight line, all equally spaced, if these were chemically homogeneous, non-rotating, non-magnetic stars without mode interactions. But they aren't. These are evolved stars, so they are not chemically homogeneous. No, what we find is a much more complicated period spacing pattern than before. But don't worry, we can basically ignore this part for now. So this is actually the mode mixing I mentioned before. So these are pressure modes and gravity modes that are interacting. They're not really interesting for us now if we want to look at period spacing patterns, but what we are interested in is in this part of the period spacing pattern. And just as before, we see kind of this wavy bunny hop pattern because of chemical stratification within our genuine single star. If we now add the period spacing pattern for our merger product, we see that, remember for the main sequence star, there was a very slight difference in the mean period spacing. Here we see that the modes are twice as closely spaced in the merger product than they are in the genuine single star. And there are these weird deep dips in the period spacing pattern for our merger product, which are not here for a genuine single star. So these dips, very quickly about that. So this was something that we first thought might be numerical, but what we actually found is that just like you have mode interaction, mode mixing here between P modes and G modes, which live close to the core and in the envelope, these dips are caused by G modes living in this inner mode cavity, tunneling through our convective shell over here, just like quantum tunneling, and then interacting with G-modes that live in this outer cavity. So this is, at least up until a certain mass, a very, if we were ever able to observe this, this would be a very kind of smoking gun kind of feature to find in a period spacing pattern and allow us to identify merger points. There is a few buts. I don't want to spend too much time on this. So this was a very basic study. Well, we didn't take into account magnetic fields, even though they might be generated by such mergers. They might suppress these predicted gravity modes. So yeah, that's something we need to take care of and look deeper into. Another thing is that our genuine single stars, or the classical Hertzsprung gap stars here, if they have masses above or around 12 solar masses, they also tend to have a convective shell, which also gives them these deep dips in their period spacing pattern over here. So that kind of loses its diagnostic power. And so far, these modes that we predict here with Gyre, they have not been found in blue supergiant stars so far. Maybe with new data, for example, from PLATO, who knows, we might be able to detect them, but so far there's no observational counterpart yet. What is detected in such stars in blue supergiants is a stochastic low frequency variability. So this is a very low frequency. There is this kind of excess in power, which there is really strong debate going on what the origin is, but who knows, maybe the origin has to do something with these convective shells that we predict. But yeah, the last thing has not been said about that yet. Okay, and then for those who thought that I forgot about the other objects that we were going to talk about today are accretors. Do not be alarmed or be happy. So let's forget about the mergers for a moment and now focus on the accretors. So first thing, it's a bit similar to what I just told you about the mergers, is that our stellar pulsations are sensitive to the chemical composition of a star. And this is a very general statement. And just like we could have chemical enrichment in our main sequence merger product because the helium-rich core ends up in the envelope of the merger product, in a similar way, when you transfer mass from one star to the other, you will eventually get nuclear fusion process material from the donor star into the envelope of the accretor. So your accretor's envelope is also going to be enriched in heavier elements. And what Amadeus Misuda found already in 2021 and 2022, by modeling two eclipsing binaries. So they started from observations of delta Scuti stars. And they found that in order to actually model these stars, you needed a kind of a slight shift in the mode frequencies. And they also found that if you predict the modes, assuming that it's a single star, or you look at the observations, that some of the modes are actually not excited. No, that's not what I wanted to say. So basically, they find modes that a single star model does not predict, right? But if you assume that this is an accretor star with a chemically enriched envelope, you're actually able to excite. So excitation is a physical mechanism that actually puts energy into your modes. So having these extra metals basically in the envelope causes that some modes are excited in the model predictions where they are not excited in a single star model, right? So I think I butchered this a bit, but what you need to remember is that you need to basically model post-interaction binary components with binary models, right? Because if you assume that there are single stars, it's not going to work out. Okay, that was the envelope. Now let's focus more on the near core region again, just as we did for the merger products. So what actually happens during such an accretion phase? So we have a star here, massive star, radiative envelope, and a convective core. And as I mentioned a few times already today, when the star evolves, the convective core shrinks and leaves behind this chemical composition gradient. And as I told you also before, this chemical composition gradient causes this peak to appear in your Bruns-Väisälä frequency, which then influences your gravity modes. Okay. Now, when a star accretes matter, so we dump a bit of matter on the envelope, and it settles, the core tries to expand. It's a more massive star now, so the core should also expand and take on a size that is appropriate for its new mass. So if a star does that, we call it rejuvenation because more fresh hydrogen is being ingested in the core. Um, your core grows, and then eventually, after mass transfer, the core is going to shrink again, just like it did before on the main sequence. So what Tom Wegg and collaborators found in like 2 years ago is that such a rejuvenation phase during mass transfer leaves you with Bruins-Weiss stellar frequency profiles that again do look very different from those of genuine single stars. So the genuine single star here is in orange, what we expect, a single peak. But if you model an accretor that looks the same from the outside, you find that they actually have these two peaks in their Bruins-Weiss stellar frequency profile. So two peaks in the Bruins-Weiss stellar frequency profile, just like in our merger product before, will give you additional components in the variability of your period spacing patterns. So these are period spacing patterns. The purple ones are for the accretor product. And you see that they do not really follow the kind of the morphology of those of the single stars in orange. And they also seem to be a kind of phase shifted. So also here, for our accretors, we see that the effect of accretion is to introduce additional variability in your period spacing patterns. Quickly going to go through this one just to show you that this has been repeated, this experiment, for example, for a more massive accretor where you find a similar kind of additional components in the variability. And it's also been done for kind of slower mass transfer phases for different masses. So this is definitely also the previous one also, but this is also definitely a paper you should check out because they try different configurations of these accretors, but essentially what you always get is a Bruins-Weiss stellar frequency profile with two peaks, so additional variability in your period spacing patterns. This brings us a bit at kind of an awkward situation now because we find that both main sequence merger models and main sequence accretor models have these additional components in their variability. Now, why this is awkward is that something that people that work on binaries like to ignore is that it's not only binaries that are very common, it's actually these higher order multiples that are very common at high masses. So if you have a triple star and two of the components in that merge, which in Floris et al. Paper from last year, they predict that this actually occurs quite often. So if you have a triple in which two components merge, you will end up with a binary where one component is actually a merger product and not necessarily an accretor star. So given that they have very similar, how should I say? We predict that they both have additional variability in their period spacing patterns. We might not even be able to say if this is an accretor or a merger product after all, but we will be able to say that it is a binary interaction product. So one way out of this problem might be this is kind of a relatively new technique that was developed also very recently, is that we're dealing with a variability in a certain signal, right, with a certain period and a certain amplitude. So what Zhao Guo realized, for example, is that why not take a Fourier transform of a period spacing pattern, which is ironic because Fourier transforms is what we take to actually go from our light curves from space missions, for example, to our frequency space. So we essentially do it again. We take a Fourier transform of a period spacing pattern, and this is going to give you the frequency or the location within the star where you expect, this is going to be, I need to start this again. This is going to allow you to quantify kind of the frequency of the variability. So how often a certain component is there in a period spacing pattern. And it's also going to be able to link which regions within the star are responsible for for certain components in your variability. For example, we have two components in for the single star. We have one component in the period spacing pattern, so this bunny hop pattern, and we find that there is one dominant peak in this orange shaded region, which is a Fourier transform of our period spacing pattern. For the merger product or the accretor in this case, we have two components in the period spacing pattern, which you also clearly see show up here by these two peaks in the Fourier transform. And we find that these peaks also correspond to regions where there's rapid changes in our Bruns-Weisseler frequency. So this is something to explore further, and this might help us to learn a lot more about these binary interaction products than we thought before. With the last few minutes that I've left, I just wanted to say that there's still much to consider also with this accretor seismology. So one thing I said is that when the star accretes matter, its convective core grows, right? It rejuvenates. Turns out this is not a given. The convective core tries to grow, but this chemical composition gradient over here typically prevents your convective core from growing. So the rejuvenation, whether or not the star rejuvenates and by how much, depends very much on the near core mixing, for example, semi-convection, convective boundary mixing. And so this is something that together with Ronnie Baumann that I looked into, like how do these results, for example, from the WEG 2024 paper change when we change the semi-convection or the convective boundary mixing. So we're quickly going to go through this, but essentially we find that there is a whole spectrum of different features that you get, so that we're not at a general kind of general way of identifying the signatures of accretion yet, because there are so many uncertainties in our stellar models to this day. Another thing that we also found is that the core during and right after accretion is very sensitive to how the thermal equilibrium in the star is doing, right? If you have very fast mass transfer, your star will be out of thermal equilibrium, and the core tends to, just like in our merger product, tends to have a transient behavior where it grows and shrinks again. If mass transfer is slower and the star is in thermal equilibrium, we don't get this behavior so much. But this is really going to affect what happens to these features you get in your Bruns-Weisseler frequency profile. And then one thing that I should definitely mention is that, we're talking about accretors here. I told you at the beginning, these are probably things that show up as BE stars, so they should be rapidly rotating. So we should repeat these studies, including rotation for sure. Then in the last minute, let's get to the summary. So what I showed you is that a blue supergiant merger product should be identifiable by the mean period spacing and these dips in the period spacing patterns, but only if we actually observe these modes, that they're actually excited, that they're not suppressed. So there's a lot of buts there, but if we get good data of those, we might be able to identify blue supergiant products, whether they're mergers or not. For one main sequence merger product simulation, I remember we only had this one 3D model, but we should try to repeat this for many more. But from this one simulation, we found that there should be measurable shifts in the mean period spacings and the P-mode frequencies, and that there is this additional component in the period spacings. And then for rejuvenated accretors, we found that they also have such an additional component in their period spacings, but that they depend strongly on our assumptions for mixing and the type of mass transfer. So in general, lots of more configurations to explore, both for the mergers and for the accretors, but we're going to need better 1D models to do that. The behavior of the convective core was really kind of played a key role in this whole story, because it really changes how the near core structure looks like. And I would say that now that we have at least an idea of what we need to look for, it's time to look at the data, maybe even with PLATO data, and see what we can find, and hopefully solve this mystery. So thank you, and sorry for going over time for a few minutes, and I'm happy to take any questions.
Great. Thank you very much, Jan. I see several applause reactions from online participants. So we have some time for questions. Yes, yeah.
Hello, Jan.
Hi.
I have I don't know, it may look like a stupid question, but if you have mass transfer from one star to the other, both star will be affected. So have you looked at what happened to the mass donor? And is there anything, I mean, it would be easier if there was a kind of signature in each, right? And so in this case, you could identify both things in two star and say, okay, there is no question, it's that. So have you looked into that?
I haven't looked into that. I know, I think people are, but it's not been something that I looked at. But yeah, just from the fact that indeed you get a donor star that strips its envelope, it will pulsate very differently from like a regular May sequence star. But yeah, so combining those would be ideal, right? Because then we could, for example, say, well, there is clearly has been a past mass transfer phase. So this thing with the multiple components in its period spacing pattern is likely going to be an accretor instead of a merger product. So yeah.
Thanks.
All right. Other questions for Jan? So I have a small question. So you alluded to it at the very end regarding the need to look for data, but you also mentioned kind of a case of a star that's strongly suspected of being a merger, HD 148937. In that case, do the asteroseismic signatures kind of resemble some of your predictions, and has that been seen in other suspected merger products?
Well, in the case of this massive magnetic component in the binary that you mentioned, as far as I understand, this is the moment that they captured this star is only, what is it, like a few thousand years after the merger, or the suspected merger. So it's just not it's still relaxing basically. It's still in this relaxation phase. I don't know if you remember from the merger product simulation from Fabian Schneider, you had the HRD before the star becomes a main sequence star again. It does this whole excursion where it expands and it rotates really quickly. So the fact that there's also still this remnant around of the outflows, it probably isn't in a state where we can get asteroseismic data from them, but why not try? I've had this question before, so yeah, we could see. And then for other stars, well, the only thing that I know of is that there are these weirdos out there. There are period spacing patterns with weird features that we can't seem to explain, that people maybe even haven't tried to analyze. So it could very well be that these are accretors or are merger products. But yeah, we still need to explore.
Great, thank you. Other questions for Jan? We still have a few minutes if people have questions. Okay. Well, in that case, thank you, Jan, for a very clear and interesting presentation. This was this was really great and some nice work to look forward to in the coming months to years, especially with PLATO coming up. I'll take the opportunity to remind everyone that our talks are recorded and that the recordings are available sometime later on our YouTube channel. So if you have missed talks in the past, or you have colleagues who couldn't make it to this talk, please make sure to take advantage of this resource. I also point out that this was our last seminar of the 25-26 academic year. And so thank you for joining us throughout the year. We hope you've enjoyed our seminars, and we'll look forward to resuming them in the fall. So thanks again, Dr. Jan Henneco, for a wonderful talk, and thanks you everyone for joining us.
Thank you for inviting me, and thanks for being here, everyone.